So we start this lecture series with some definitions. The first definition is of a homotopy. So say you fix two topological spaces X and Y and there are maps between them F and G. We want to define a homotopy between F and G. So by a homotopy we mean a continuous map. So by a homotopy from F to G we mean there is a continuous map. So you denote this map by H, and this map goes from X times the unit interval 0 to 1 to Y. Denote this map by H such that H of X comma 0, this X is from space X and 0 is from the interval. This is equal to F of X, and H of X comma 1 is G of X. So that is pretty much it. Now F is homotopic to G, so this is the symbol for homotopic. If there exists a homotopy H as we have just defined above. Number 3 is, say two spaces X and Y are homotopy equivalent. So now we are talking about spaces, not maps. So notice the distinction. X and Y are homotopy equivalent if there exist continuous maps. So we have two continuous maps. You go from X to Y by a continuous map J, and then you come back to X from going from Y to X via continuous map K. And the condition is that first you apply J, that is go to Y and then come back to X by applying K. This is homotopic to ID on X. And then you first apply K and then apply J, you get homotopic to ID on Y. So let us now explore the first lemma. Homotopy gives an equivalence relation on the set of continuous maps from X to Y. So homotopy gives an equivalence relation on set of continuous maps from topological space X to topological space Y. So let us prove this. So F is homotopic to F itself by the homotopy. You just have H of X comma T is equal to F of X. Here small x comes from topological space X and T comes from the unit interval 0 to 1. So you just have H of X0 is F of X, H of X comma 1 is F of X. So if F is homotopic to G, now we have to show G is homotopic back to X, that is reflexivity. Now this you can show by constructing a new homotopy H prime, which is nothing but H of X comma 1 minus T. So we need to check H prime X of 0 should give you G of X. So H prime X comma 0, this is equal to H of X comma 1, which is equal to G of X, and then H prime X of 1 should give you F of X. And as you will see, this is equal to F of X. So we have reflexivity, and finally we have to check transitivity. So say F is homotopic to G by some homotopy H, and G is homotopic to map H by some homotopy H bar. Then F is homotopic to H by the following homotopy. So H X comma 2T when T lies between 0 and half. So this will be a continuous map. Notice that when t lies between 0 and half is actually precisely meaning that 2t lies between 0 and 1. So we have done nothing. We have taken the homotopy. We first 0 to half, we travel with homotopy h, and then we travel with homotopy h bar from half to 1. So when t is 0, you get f, and when it becomes 1, you get h. Again, notice that 2t minus 1 has to lie between 0 and 1. So we are basically rescaling. So this is important, and this will come up again and again. So you should know 0 less than equal to t less than equal to half is equivalent to 0 less than equal to 2t, which is less than equal to 1. And similarly for 2t minus 1. And that is how you get 2t and 2t minus 1. Both 2t and 2t minus 1 have to lie between 0 and 1, because they are the original homotopies which we have rescaled. Now let us give an example. Say you have general linear matrices and you have two maps f and g, and they map it to a 2n by 2n matrix. So we need to show f and g are homotopic to each other. So we are given f of a, b as the following matrix and g of a, b as the following matrix. So the homotopy is, if you put t as 0, you will get f. If you put t as 1, you will get g. So this is the homotopy. You have cos t minus sin t, cos t, 1 0 0 b, and then cos t, and then finally you have sin t minus sin t and cos t. So notice that we take t from 0 to pi by 2. So if you plug in 0 and pi by 2, you will get respectively f and g. So you can rescale this to make it from 0 to 1. So say you put capital T from 0 to 1 and you appropriately then multiply by 2 by pi, and then you can plug in and you will get a 0 to 1 scale. But this is easier to understand from 0 to pi by 2. Now the topology on the matrices is just, these are just identified with, say, induced topology on R m by n. Yeah. So you can just identify a general linear n by n matrix by R to n. So nothing much here.